In this unit, we're going to begin by looking at sequences, which are simply lists of numbers. The first type of sequence that we'll look at is an arithmetic sequence. An arithmetic sequence is a list where each term is found by adding a constant to the preceding term. That constant is what we call the common difference, and we'll refer to that with the variable d. All right, so to determine if a sequence is an arithmetic sequence, we're going to take a look at the differences between the terms. 7 and 3 have a difference of 4, but it's important to know that if you added to 7, you would add -4 to it, and then we would add -4 again to get to -1, and -4 again to get to -5. So this is an arithmetic sequence, and it has a common difference equal to -4. It's important to pay attention to the sign of that common difference. Are the terms increasing or decreasing? All right, let's take a look at the next sequence. From 5 to 6, we have a difference of 1. 6 to 8, we have a difference of 2. And then 3, and then 4. There is a pattern here, and we could predict the next term in the sequence, but it is not an arithmetic sequence. So all I'll say about this one is it is not arithmetic. Turns out this type of sequence with a pattern of differences that all have a common difference of 1, the differences themselves form an arithmetic sequence, that's called a quadratic sequence. All right, try the one below on your own, 1, 2, 4, 8. Pause the video while you do this. So it turns out that this sequence is not arithmetic either. We don't have a common difference between the terms. Now try the next one. You should have found that this sequence is an arithmetic sequence with a common difference of 3, since each term increases by 3 over the previous term. Now we're going to see if we can put this pattern into a formula. So in example 2, we're finding the 100th term of this sequence. Now, what I don't want to do is I don't want to say, oh gosh, I'm adding 2, and then I'm adding 2, and then I'm adding 2, and list 100 terms. But let's see what we can do to establish a pattern. Now we're going to use a table of values very similar to what we did when we were working with exponential functions. Our table headers here are going to be n and a sub n. Let me define those for you real quick. N is going to stand for the number of the term. In other words, n is 1, gives us the first term of 3. N is 2, gives us the second term of 5, and so on. Now a sub n is the value of the term, and so now let's concentrate on not what the actual term is, but how we get there. What is the pattern? Now, as we said before, we're adding 2 to the previous term, so 3 plus 2 gives us the second term of 5. For the third term, we have 3 plus 2 plus 2, or 2 times 2. For the fourth term, 3 plus 2 plus 2 plus 2, or 2 times 3. Now let's go ahead and put in the values that are hidden. And we can see, whoops, that should be a 2 times 0 on the first row there. So now what we can do is we can see that there's a pattern here. It appears that the a sub n's, or the nth term, is equal to 3 plus 2 times something that changes each time. And now what I want to do is address how that something that the 2 is being multiplied by is related to the term number. Take a look at each of those entries, and what you'll observe is that the entries in the a sub n column, 0, 1, 2, and 3, are all 1 less than the entries in the n column, 1, 2, 3, 4. So the number that 2 gets multiplied by is the term number minus 1. So for instance, if I want to find the 100th term, which is what we were asked for originally, that would be 3 plus 2 times 100 minus 1. And we can use a calculator to do that. So on your calculator, you can add 3 plus 2 times, and we might as well go ahead and do the subtraction in our heads, 99 equals 201. So the 100th term is equal to 201. Thankfully, we didn't need to list 100 terms to find that. That brings us to generalizing the nth term of the arithmetic sequence, which is the value of the first term plus the common difference times the number of the term minus 1. Some things to define here. A sub 1 is what we use to define the first term of the sequence. A sub n is the nth term of the sequence. D is the common difference, and n is the number of the term. All right, so take a look at example 3. We're going to consider this arithmetic sequence 4, 10, 16, 22. What we can observe about this sequence is that the first term is 4, and that common difference is 6, since we have to add 6 to get from one term to the next. So, remember our formula for the nth term of an arithmetic sequence. We are looking for the 25th term, so we'll call that a sub 25, which means that we are replacing the n with the number 25. A sub 1 can be replaced with 4, the d, the difference, can be replaced with 6, and we can replace the n on the right side with 25 also. Now we just have some arithmetic to do. Let's grab the calculator again and enter that computation in the calculator all at once. And you can certainly enter it in if you don't want to do that subtraction in your head. You can just enter it in as you see it on the page, and we get 148 as the value of the 25th term. So a sub 25 equals 148 means the 25th term is 148. Now in B, we're looking for which number term is 604. Well, this time we actually have the value of a sub n. Same formula, but this time the thing that we know is the value of the term. We just don't know what term number it is. A sub 1 is still 4, D is still 6. And so I think the easiest way to solve this one is to subtract 4 from both sides, divide by 6, and add 1. So which number term is 604? The 101st term is my answer. By the way, you can distribute first if you like before you start to solve for n in that equation. Either way, it'll work out the same. All right, below, try A on your very own. Find the 30th term in this sequence. All right, you should have found that the 30th term is equal to negative 80. Now try B, where you're trying to find the term number. So we should have found that the 47th term is the one that equals negative 131. All right, now let's take a look at a different type of sequence. The second type of sequence is a geometric sequence. A geometric sequence has a different pattern. In a geometric sequence, it's a list of numbers where each term is found by multiplying this time by a constant to the preceding term to get the next term. That constant is called the common ratio, which we'll refer to as R. All right, so in 4, we're determining if each sequence is arithmetic, geometric, or neither of those. If it's arithmetic or geometric, finding the common difference or the common ratio. So what we can see in A is this is not an adding pattern. This is actually a multiplying pattern where we multiply each term by -2 to get the next term. And so this is a geometric sequence with an r equal to -2. When you have a negative r value, your terms will oscillate back and forth between positive and negative. All right, let's take a look at what's going on in the next sequence, 1, 4, 9, 16, 25. The numbers are not increasing by the same amount each time. 1 to 4 increases by 3, 4 to 9 by 5, by 7, and then by 9. It's not strictly a multiplication, so 1 times 4 is 4, but then the next term would be 16 if we were multiplying. So it appears to be neither of those types of sequences. In C, we may benefit from giving ourselves a common denominator here. So 4 is 8 halves. -1 is -2 halves. And -6 is -12 halves. And if we do that with this sequence, what we can observe is that our numerators are decreasing by 5. So each term is decreasing by 5 halves. That makes it an arithmetic sequence with a common difference of -5 halves. Since our terms are decreasing, that means we're adding a negative number each time. All right, try A below on your own. Hopefully you found an arithmetic sequence with a difference of 2. Now try B. This one turns out to be neither arithmetic nor geometric. 2 times 3 is 6, but 6 times 2 is 12, so we don't have a common ratio to get from one term to the next. We're adding 4, 6, 8, and 10. So there's a pattern there, but it's not an arithmetic sequence because we're not increasing by the same amount each time. All right, try C. All right, this one was a geometric sequence with an r equal to 1/5. Now, our r is a fraction that is between 0 and 1 because we have positive terms that are getting smaller each time, right? We're multiplying by 1/5. If we were multiplying by 5, the terms would be getting bigger. All right, let's check out another example. We're going to generalize here again, just like we did for arithmetic sequences. So we're asked to find the 16th term in this geometric sequence. And of course, we could list out all the terms. But again, let's start with a little table of values. And we're going to put our n, our term number, in the first column, and a sub n, the value of the term, in the second column. So the first term has a value of 3. The second term has a value of 3 times 2. And the third term has a value of 3 times 2 times 2, or 2 squared. And the fourth term has a value of 3 times 2 to the third power. Right? We keep repeatedly multiplying by 2 each time. Let's take a look at our hidden numbers in the first couple of entries. In the second row, we have 3 times 2 raised to the 1 power. And in the first row, we have 3 times 2 raised to the 0 power. What you can observe about those exponents is that they're all 1 less than the term number. So in general, a sub n is 3 times 2 raised to the 1 less than the term number. If we want to find the 16th term, that would be 3 times 2 raised to the 16 minus 1. And now we need our calculator. And so 3 times 2 raised to the, and that's just going to be the 15th power. Might as well do that part in our heads. So the 16th term is 98,304. That brings us to making a generalization about the nth term in a geometric sequence. The nth term in a geometric sequence is the value of the first term, times the common ratio raised to the n minus 1 power, where a sub 1 is the first term of the sequence, a sub n is the nth term, r is the common ratio, and n is the term number. So now let's put this to use. Here's a geometric sequence 3, 6, 12, 24, the same one that we were working with before. And we want to find the 7th term in the sequence. So since it's geometric, we're going to use the formula for the nth term of a geometric sequence. And we're looking for a sub 7, the 7th term of the sequence. We can make some substitutions. A sub 1 is the first term, that's 3. Looks like the ratio is 2. And so since we replaced n on the left with 7, that means that we can replace n on the right with 7 as well. So a sub 7 is 3 times 2 raised to the 6th power. So 3 times 2 raised to the 6th power gives us 192. And that's the value of the 7th term of the sequence. All right, in 6, we are looking for the number of the term that equals 6,144, and we don't want to have to list out all those terms. In fact, I'm going to ask that you write down an equation for each. So our equation is a sub n is equal to a sub 1 times r raised to the n minus 1, and our term a sub n is 6,144. First term is 3, ratio is 2. Now what we need to do is to solve for that n, which lies in an exponent. So in order to do that, we're going to use logarithms. But before we do that, we have to isolate the exponential expression, 2 to the n minus 1. In order to do that, we need to divide by 3 first. So we have 6144. Oops. 6144 divided by 3 is 2048. So 2048 equals 2 to the n minus 1. And if we want to solve for an exponent, that is a logarithm. So the log base 2 of 2048 equals the exponent n minus 1. And our logarithm here is something we can enter in the calculator. So control 10 to the gives us a logarithm. We can enter the base of 2. And in the argument of the logarithm 2048, and that's equal to 11. So 11 is equal to n minus 1. That gives us n is equal to 12. So which number term? The 12th term has a value of 6144. All right, try A below on your own. The 6th term equals 486. And now try B, where we're looking for the number of the term that's equal to 1,062,882. So we should have found out that the 13th term has that value. All right, one last thing that we're going to take a look at is what are called means. Now I know you know the concept of an arithmetic mean, which is just actually the average. But another way to define mean is it's a number that falls between two others in an arithmetic sequence. A geometric mean, similarly, is a term that falls between two others in a geometric sequence. So, in example 7a, we're asked to find the arithmetic mean of 4 and 16. So what I'm going to do is I'm going to create an arithmetic sequence here, but I'm going to insert one blank in between 4 and 16. The arithmetic mean is the number that comes in between them in an arithmetic sequence. Now, in an arithmetic sequence, to get from term to term, we add d. So add a d to get to that blank, add another d to get to 16. That suggests an equation, 4 plus 2d is equal to 16. So subtracting off 4, we get 12. And that gives us a difference of 6. So now we just insert our number into that arithmetic sequence by adding 6. So 4 plus 6 is 10. There's our arithmetic mean. Incidentally, that is the average of 4 and 16. All right, let's take a look at a geometric mean. In a geometric mean, we're going to approach it similarly, but just with a geometric sequence. So the geometric mean of 4 and 16 will set up something similar, 4 blank 16, in a geometric sequence. But remember, to get from term to term in a geometric, you multiply by the common ratio. So times r gives you the blank, times another r gives you 16. That suggests an equation that 4 times r, or times r squared, is equal to 16. Let's divide by 4 and take a square root. We'll assume the positive square root. So our common ratio is 2. So 4 times 2 is 8. 8 times 2 is 16. That forms a geometric sequence. So you notice that we get two different numbers here. The arithmetic mean between 4 and 16 is 10. The geometric mean is 8. We can do that with more than one mean if we wish. So in example 7c, we have 3 arithmetic means falling in between 3 and 31. So we're going to do that similarly. I'm just going to put 3 blanks in between 3 and 31. And then remember that we're forming an arithmetic sequence, which means that we're adding d. So adding d, adding d, adding d. Be careful how you write these. Make sure that it's organized. In order to have 3 blanks in between them, we have to add 4 d's. So to get from 3 to 31, add 4 d's to the 3, and that equals 31. Let's solve. 4d is equal to 28. So d is 7. So we're adding 7, 10, 17, 24, 31. Here are our 3 arithmetic means. Now we're going to do one with geometric means. So we have 2 geometric means between 5 and 40. So 5 blank blank for our 2 geometric means, and 40. To form a geometric sequence, we have to multiply by r. So that suggests an equation. 5 times r cubed is equal to 40. Divide through by 5, and we get r cubed is equal to 8. So r is 2. Our 2 geometric means are 5 times 2 is 10, and 10 times 2 is 20. And then just as a check, 20 times 2 is equal to 40. All right, try E below on your own. 4 arithmetic means between 2 and 17. Those 4 arithmetic means are 5, 8, 11, and 14. Now try F, the 3 geometric means between 3 and 1/27. And those 3 geometric means are 1, 1/3, and 1/9. Right, in example 11, we are given some other information here. We have the 5th term of an arithmetic sequence, and we also have the 11th term. Now, to get from the 5th term to the 11th term, we're going to have to add. So the 5th term plus 6 common differences, so 6 times d, is equal to the 11th term. Notice that that number 6 is just the difference between the term numbers. To get from the 5th term to the 6th term, you have to add 1d. To get from the 5th to the 7th, you have to add 2 d's, etc. Well, we know the 5th term is -3. We don't know the difference, but we do know the 11th term is 21. Okay, now we can solve. Add 3 to both sides and divide by 6. The common difference is 4. That's one of the things that we were asked for. And then we are going to use this information to find the first term. Now, if we start with the first term and we're working toward the 5th term, we're going to add 4 common differences because the difference between 1 and 5 is 4, so there are 4 differences added. So we don't know what that first term is, but we sure know that 4 differences is 4 times 4, and the 5th term was something that we already knew was -3. So a sub 1 plus 16 equals negative 3, and that means a sub 1, the first term of the sequence, is negative 19. All right, let's try something similar with a geometric sequence. So in this one, the third term of a geometric sequence is 7, and the eighth term is 1701. So if we're going from the third term to the seventh, we're going to have to multiply, since this is a geometric sequence. But we're going to multiply by r 5 times, to get from the third to the eighth term. So a sub 3 times r to the fifth is a sub 8. Notice the difference between 8 and 3 is 5. That's the exponent of r. So the third term is 7, and the eighth term is 1701. Let's divide by 7. So r to the fifth is 243. Now we have to take a fifth root, and there's a couple different ways that you can take a fifth root. You can use the nth root button on your calculator, which is Control and the caret key. So then you'd have to fill in the fifth root here and fill in 243. You can do it that way. Or you can also raise 243 to the 1/5 power. Either way is going to give us a value of 3. So we've got the common ratio. That's one thing that we were asked for. And then we're using that information to find the first term of the sequence. Now the first term gets multiplied by r and by r again to get to the third term. So a sub 1 times r squared is a sub 3. Notice the difference between 1 and 3 is 2. That's the number of r's that we have to multiply by. The first term is not known. The ratio is 3, so r squared will be 9. And a sub 3 is 7, so that means that a sub 1 is 7/9. That's all of the information for the first lesson of this unit.